This is section 3.2, part B. We're going to be looking at finding equations for exponential functions. And I'd like to start by looking at the pattern that we create when we make a table of values for an exponential function. What we're seeing here are x values that are all increasing by exactly 1. And we're going to calculate the y values. If I have 2 times 4 to the x as my function, this would be 2 times 4 to the negative third, which is the same as 2 over 4 cubed, 2/64 or 1/32. I can keep going. 2 times 4 to the negative 2 would be 2 over 4 squared. That's 2/16 or 1/8. And 2 times 4 to the negative first is just 2 over 4 to the first. 2/4 would be 1/2. After that, it gets a little easier to do mentally here. 4 to the 0 would be 1. 2 times 1 is 2. 4 to the first is just 4, so 2 times 4 would be 8. 4 squared is 16, times 2 is 32, and 4 cubed is 64. Doubling that would give me 128. All right. So again, our x values here were very carefully chosen to increase by exactly 1. Take a look at the y values. Do you see a pattern in those at all? It's really easiest to see probably with the whole numbered ones rather than the fractions. Most of our brains just think more easily in terms of whole number arithmetic. But as I come down here from 2 to 8, from 8 to 32, from 32 to 128, can you see that all these y values are being multiplied by 4? The fact that the multiplier of 4 is no coincidence. 4, remember, was actually just the base of our exponential function. So if I've got a table of values where the x's go up by 1, and the y values are consistently being multiplied by the same thing every time, what I have is a table of values for an exponential function, and the constant multiplier gives me the base. One other thing to point out here, look at this line right there. When x is 0, y is 2. And notice 2 is really just the multiplier a in the exponential function. So I can identify that just by looking at the table as well. So to summarize, we can conclude that to find an exponential function of the form f of x equals a b to the x, what we need to do is find a and b, where a is really just the y-intercept. It's what happens when x equals 0. B is the constant multiplier when x increases by 1. So it's the constant multiplier on y when the x's are going up by 1. All right, let's use that idea to come up with exponential functions for a couple of tables of values on the next page. I'll double check, yes, my x's are going up by 1. And when I look at these y values, the first thing I'm going to notice is actually instead of multiplying, it kind of looks like these are being divided by the same thing, namely 3. As I go here, dividing by 3, dividing by 3, dividing by 3, and so on. However, according to what we said on the last page, it has to be a multiplier. Keep in mind that division is really just multiplication by the reciprocal. So instead of thinking of this as division by 3, I'm going to think of it as multiplication by 1/3. Write a few of them out here. I won't write them all. So what that tells me is that b is 1/3. I also have the y-intercept in my table, 0, 9. So what that tells me is that a is 9. And that means that if I would like to write my function f of x in the form ab to the x, I will have 9 times 1/3 to the x. All right, let's try one more. Double check again. The x's are indeed going up by 1. This method doesn't work if they aren't. And I, again, need to take a look here at what's happening to my y values. It's easiest to see with the whole numbers. So come on over here and let's start at 2. Can you see what the pattern is, what the multiplier is? Looks like it's times 5, right? Now I'm sure that's also true down here in the decimals. It's just a little harder for our brains to process that as quickly. So b is 5. The y-intercept right here gives me an a value of 10. So writing my exponential function, f of x equals ab to the x, I'll have 10 times 5 to the x power. All right, that is the end of part B.